Futures are a very general pedagogic concept, but now we need to learn how we can implement them in Java, and that's where the ForkJoin framework that we had seen earlier in Java 8 can be very helpful. So as before, we can create a class, and let's say it's called asum. But now if you want to use futures, we have to say that this class extends recursive task, not recursive action, which is what we saw earlier with task parallelism. Now, once we have that, there'll be some fields, of course, and they'll, in the case of the array sum example, we have a reference to the array, we have a low and a high for the range, and earlier when we were doing imperative tasks, we actually had a field for the sum. As we'll see, we don't need that over here because the sum will be encoded in the return value. So then what we need to do is we need to define the compute method for the asum object. And in the compute method, we have to check the boundary conditions as before. So if, for example, low is greater than high, then we have to return 0 because that's an empty range. Else, if low is equal to high, then we just have a singleton and we can return the array element at that position. Else, and this is the interesting recursive divide and conquer part, we have to figure out what to do in terms of using futures. Well, as before, we compute the midpoint, which is the sum of low plus high divided by 2. We create new objects for the left half of the array, which would go from low to mid with array, and the right half of the array that we want to compute the sum of, where it'll go from mid plus 1 to high and also pass array. Now what we can do is we can spawn the computation of the right half of the array as a recursive future task, and there we just have to use fork, just like we did before. And so this is really launching the future. And then, and this is the more elegant part compared to the last time, we can just return the sum of the value computed for the left half of the array and r.join. So what join does, as we know for futures, is it actually implements the future get operation. And this comes about because a recursive task over here implements the future interface in Java, and so join actually has a return value. Earlier with imperative tasks, we saw that join was something that we could use to implement finish and just wait for a task to complete. But here with functional parallelism and futures, join actually returns the value that's computed. And now we can reason about the computation graph in this case because at least for one recursive call, we have the left executing sequentially. We have the right part spawned. So this is in the start. And then over here, when we accumulate the sum, we have the join, which returns the value and ensures that we only compute the sum when the right subcomputation is completed. So there you have it. Once you have the pedagogic concept of futures and you've already had some experience with the ForkJoin framework, the main extension is to use recursive task, not recursive action. And then you have return values, and then the join method call, which we had seen earlier, now encapsulate the return values. And with this, any general algorithm that you see using futures can be implemented in Java using the ForkJoin framework.